Hello, and welcome to Space for Sleep. There is nothing in ordinary experience that prepares you for a total solar eclipse. Not really. You can know the geometry. You can know the date. You can know the path of totality down to the kilometer. You can stand outside with certified eclipse glasses, watch the moon take its first small bite from the sun, and tell yourself that you understand exactly what is happening. The moon is moving between Earth and the sun. Its shadow is falling on the planet. You are waiting for the darkest part of that shadow to reach you. And then the light begins to change. Not like sunset, not like storm clouds, not like evening. The landscape remains visible, but something in the color of the world has gone wrong. The light becomes flatter, thinner, colder. Shadows sharpen. The temperature falls. Birds and insects may begin behaving as if the day has ended too quickly. People who were speaking a few minutes earlier often grow quiet, because the event no longer feels like something on a calendar. It feels physical. Then, in the last seconds, sunlight breaks into beads along the mountains and valleys of the moon. A final point of white light flashes at the edge of a black disk. The diamond ring appears, and then the sun is gone. The corona appears. This moment is the center of the experience. The sun that people normally know is the photosphere, the bright visible surface, about 5,800 Kelvin, the layer that emits most of the sunlight reaching Earth. But the corona is far hotter, reaching temperatures of 1,000,000 degrees or more. This is one of the great puzzles of solar physics. The outer atmosphere of the sun is vastly hotter than the surface below it, even though simple intuition would expect temperature to fall as one moves away from the heat source. The answer is connected to magnetic fields, waves, reconnection, and the restless motion of plasma. The full problem is still active science. During a total eclipse, the structure of the corona becomes visible as a map of magnetic influence. Streamers, plumes, polar brushes, loops, and long white extensions shaped by solar activity. So when the corona appears, you are not seeing a decoration around the sun. You are seeing the outer atmosphere of a magnetically active star, the region from which the solar wind flows outward through the solar system. A pale, white, structured halo surrounds the black moon, extending into a sky dark enough for bright planets and stars. The horizon glows in every direction like a strange twilight wrapped around the world. For a few minutes, Earth is still beneath your feet, but it feels as if the ordinary agreement between sky and ground has been suspended. This is why total solar eclipses matter. They are not only astronomical events. They are direct experiences of celestial mechanics. They show the solar system moving in real time, not as a diagram, not as a model, not as a line in a textbook, but as a shadow passing over your own body. The sun, the moon, and Earth become a single visible machine. The science is rich. Orbital geometry, lunar distance, the corona, the chromosphere, the Saros cycle, ancient prediction, helium, general relativity, solar physics, animal behavior, ionospheric changes, and the future disappearance of total eclipses as the moon slowly recedes from Earth. But the power of a total eclipse begins before the science. It begins in the moment when day quietly turns to night. That gives this story a natural structure. First, the body notices the eclipse, the wrong light, the cooling air, the darkening sky. Then the mind catches up. The geometry, the shadow, the moon's distance, the cycles, the ancient records, the scientific discoveries. Finally, the two become one experience. The person watching understands more, but the understanding does not make the feeling smaller. That is the kind of science story that keeps working all the way to the end. The retention comes from that escalation. At the beginning, the viewer is pulled in by the human feeling, the wrong light, the cooling air, the corona. Then the script answers the first question, why can this happen at all? Then it answers a deeper question, why does it not happen every month? Then the story becomes historical. Ancient prediction, Saros cycles, political fear, and the rise of mathematical astronomy. Then it becomes scientific, helium, relativity, coronal physics, and Earth's upper atmosphere. Then it becomes personal again. What totality actually looks and feels like, why people chase it, and why the next eclipses matter. That rhythm matters because the topic could easily become only mechanics. Instead, each section changes the viewer's reason to keep listening. First wonder, then explanation, then history, then discovery, then future anticipation, then a final return to awe. We will move through the science, the history, the geometry, the discoveries, the future eclipses already waiting on the calendar, and the strange beauty of an event that almost nobody who has experienced once is willing to stop at once. The total solar eclipse is a coincidence, not a law of nature, not an inevitable consequence of the solar system's structure, not something that would obviously have to exist, a coincidence that happens to obtain at this particular time in the history of this particular planet. The word coincidence should not make the event feel less meaningful. In science, a coincidence can be profound without being purposeful. The apparent match between the sun and moon is not evidence that the solar system was arranged for us. It is the result of sizes and distances that happen to align during Earth's present geological era. But because the match exists, it gives us a natural experiment that has shaped astronomy, physics, culture, and human memory. Many worlds have moons. Many moons cast shadows. But the particular elegance of our total solar eclipse, the way the moon hides the bright photosphere while leaving the corona visible, is rare enough that it deserves attention. The coincidence is this. The sun is approximately 400 times larger in diameter than the moon, and approximately 400 times farther away from Earth than the moon. As a result, the sun and moon subtend nearly identical angles in Earth's sky. Both appear to be roughly half a degree in diameter. When the moon passes between the Earth and the sun in precisely the right alignment, it covers the solar disk almost exactly, and this coverage is so precise that the very outer atmosphere of the sun, the corona, is visible around the moon's silhouette without being overwhelmed by the solar disk's much brighter light. This is not a small coincidence. The sun's corona is roughly 1,000,000 times dimmer than the photosphere, the visible surface. When the solar disk is visible, the corona is invisible, drowned out in the overwhelming light. A partial eclipse, even one covering 99% of the solar disk, doesn't help much. The remaining 1% of the exposed solar surface still produces too much scattered light in Earth's atmosphere for the faint corona to be detected. Only the vanishingly brief window of totality, when the disk is completely covered, allows the corona to be seen. If the moon were slightly smaller or slightly farther away, the coverage would never be complete enough to reveal it. If the moon were larger or closer, it would cover too much, hiding not just the corona but the chromosphere, the lower atmospheric layer that produces the vivid red rim visible just before and after totality. The moon is currently at approximately the right distance, and currently is doing significant work in that sentence. As discussed in the moon episode, the moon is gradually receding from Earth at about 3.8 centimeters per year, moving away from us as tidal friction transfers angular momentum from Earth's rotation to the moon's orbit. In the distant past, the moon was closer to Earth and appeared larger in the sky, easily covering the full solar disk and producing total eclipses. In the distant future, the moon will be too far away and too small in apparent size to ever completely cover the sun, and total solar eclipses will no longer be possible from Earth's surface. We live inside a finite geological window during which the apparent sizes of the sun and moon are close enough to match that total solar eclipses of the specific character we experience are possible. The civilizations that have studied and revered total eclipses, the science that has been done during them, the discoveries they have enabled, all of this is possible because of an accident of the moon's current orbital distance. Accidents can still be scientifically useful. The asteroid impact that ended the age of non-avian dinosaurs was an accident of orbital history. The existence of Earth's large moon may have resulted from a giant impact. The specific distribution of continents shapes climate and evolution. In astronomy, many opportunities arise from configurations that were not designed but can be exploited once they exist. Total eclipses are one of those opportunities, a coincidence that became a laboratory. That is part of the adult wonder of the subject. We do not need the universe to arrange itself with intention in order for it to give us extraordinary chances to learn. Future observers on Earth, living after the moon has moved too far away, would still see the moon cross the sun, but the bright ring of photosphere would remain visible, and the corona would not be naturally revealed in the same way. We happen to be here at the right time. This coincidence is also why totality feels so perfectly designed, even though it is not designed at all. The moon does not cover the sun exactly the same way at every eclipse. Its orbit is elliptical, so its apparent size changes. Earth's orbit is elliptical too, so the sun's apparent size changes slightly during the year. Sometimes the moon is large enough in the sky to cover the sun with room to spare. Sometimes it is just barely large enough. Sometimes it is too small, and the result is an annular eclipse rather than a total one. The beauty of Earth's eclipses is therefore not a fixed property. It is a moving balance between distances, sizes, seasons, and orbital timing. That moving balance creates the variety of eclipses people chase around the world. It also gives total eclipses their emotional precision. The black disk of the moon is not much larger than the sun. It does not hide the whole sky. It does not create a long, theatrical night. It removes exactly the part of the sun that normally blinds us to the solar atmosphere. The photosphere disappears, and the corona remains. That is the strange gift of the coincidence. A body that is not luminous, not large by planetary standards, and not even especially close compared with human distances becomes, for a few minutes, the best natural coronagraph in the solar system. The geometry of eclipses is worth understanding carefully, because the apparent simplicity, moon goes in front of sun, eclipse happens, conceals a surprising amount of complexity in why eclipses are not more common. The moon orbits Earth once approximately every 27.3 days, completing one revolution relative to the stars, the sidereal month. But the moon is also moving around the sun with Earth, and the relevant cycle for eclipses is how long it takes for the moon to return to the same position relative to the sun, the synodic month, which is approximately 29.5 days. Every new moon, the moon is in roughly the same direction as the sun. You might therefore expect a solar eclipse at every new moon, occurring once per month. Eclipses don't occur every month because the moon's orbit is tilted relative to Earth's orbital plane, the ecliptic, by about 5.1 degrees. This tilt means that most of the time, when the moon is new, it passes either above or below the sun in the sky, its shadow falling either above or below Earth rather than on it. Eclipses can only occur when a new moon happens to coincide with the moon being near one of the 2 points where the moon's orbit crosses the ecliptic plane. These crossing points are called nodes. The sun-moon alignment at a node is required for any eclipse. Without it, the moon's shadow misses Earth entirely. The nodes are not stationary. They precess, rotate slowly around the ecliptic, completing one full cycle every 18.6 years. This precession is why eclipses do not occur at exactly the same calendar dates each year, but drift systematically through the calendar. The combined effect of the synodic month, the nodal precession, and the small adjustments from Earth's orbital eccentricity produces a complex but thoroughly predictable pattern of eclipse occurrence. This produces what astronomers call eclipse seasons. Roughly every 6 months, the sun appears near one of the moon's orbital nodes. Around that time, if the moon is new, a solar eclipse can occur. If the moon is full, a lunar eclipse can occur. Outside these seasons, the moon still becomes new and full, but the alignment is not close enough for shadows to meet. The moon passes above or below the sun at new moon, and above or below Earth's shadow at full moon. This is one of the most useful ideas for demystifying eclipses. They are rare at a given place, but they are not random. They are windows in a celestial rhythm, built from the moon's phase cycle, the tilt of its orbit, and the slow rotation of its nodes. The sky looks simple because it repeats. The deeper pattern is more subtle because the repetitions are never quite identical. This is one of the best places to keep the listener engaged, because the eclipse stops being only an event and becomes a pattern. A single totality may last 3 minutes, but the pattern that produces it stretches across centuries. One eclipse belongs to a Saros family. That family moves across Earth over many repetitions. It begins, matures, and ends. Each member is similar enough to be related, but different enough to be its own event. In that sense, eclipses have ancestry. A viewer who understands this no longer sees an eclipse as a random spectacular moment. They see it as one visible bead on a much longer thread. This is true of many astronomical cycles. A day repeats, but not with exactly the same sunrise. The moon's phases repeat, but not with the same distance or position against the stars. The seasons repeat, but not with identical weather. Eclipses repeat in families, but the geography shifts. The universe gives rhythms rather than copies. That is why prediction and surprise can coexist. Astronomers can calculate the path of totality, the instant of second contact, the duration, the Saros family, and the apparent sizes of sun and moon. But the human experience still contains weather, landscape, nerves, silence, and the changing corona of a living star. Any given location on Earth's surface experiences a total solar eclipse on average once every 375 years, though this average conceals enormous variation, with some locations experiencing 2 or 3 totalities within a few decades while going centuries before experiencing another. The infrequency of totality at any given location is what makes eclipse chasers travel to the paths of totality wherever they occur. To sit in one place and wait for the universe to deliver an event of this magnitude on average timescales of lifetimes is not a satisfying approach for people who have experienced totality and understand what they are missing. The shadow geometry during a solar eclipse involves 3 distinct regions. The umbra is the darkest shadow, the cone of complete shadow where the moon fully blocks the sun's disk. Anyone within the umbra sees a total eclipse. The umbra is narrow. At Earth's surface, it typically reaches a maximum diameter of about 270 kilometers, though it can be considerably narrower. The path traced by the umbra across Earth's surface as the moon's shadow sweeps over a rotating Earth is called the path of totality, and it is typically several thousand kilometers long, but only a few hundred kilometers wide. A map of a total eclipse can look deceptively simple, a dark band across a globe. In reality, that band is the result of 3 motions happening at once. The moon is orbiting Earth. Earth is rotating. Earth and the moon together are orbiting the sun. The shape of the shadow on the surface also depends on Earth's curvature, the angle at which the shadow strikes, and the changing distance between Earth and moon. The path is therefore a moving intersection between a cone of darkness and a rotating sphere. This is why eclipse prediction is mathematically beautiful. The event looks like a simple covering of one disk by another, but the path on Earth is a problem in 3-dimensional celestial mechanics. The penumbra is the larger, partial shadow where the moon covers only part of the sun's disk. anyone in the penumbra sees a partial eclipse. In the antumbra, relevant for annular eclipses when the moon is too far from Earth to completely cover the sun, is the region where the moon appears fully within the solar disk and a ring of solar light is visible around the moon's silhouette. The speed at which the umbra sweeps across Earth's surface depends on both the moon's orbital velocity and Earth's rotation. The moon's orbital velocity is about 1 kilometer per second. Earth's surface at the equator rotates eastward at about 460 meters per second. Depending on the geometry of any specific eclipse, the umbra can travel between about 1,000 and 3,000 kilometers per hour across Earth's surface. This is faster than any aircraft and faster than sound in air, which means that no ground-based vehicle can keep pace with the shadow for more than a brief period. Specialized aircraft have been used to extend the duration of totality by flying with the shadow, the most famous example being the Concorde supersonic aircraft, which participated in eclipse-chasing flights in the 1970s, allowing researchers to observe totalities of up to 74 minutes duration by flying with the shadow at supersonic speed. The maximum possible duration of totality at any given location is about 7.5 minutes, and such long totalities are rare. Long totalities require several favorable factors at once. The moon must appear large, usually because it is near perigee. The sun should appear slightly smaller, which happens when Earth is near aphelion. The observer should be near the center of the shadow path, and the geometry should allow the shadow to move relatively slowly across Earth's surface. When these factors combine, totality can stretch toward its theoretical maximum. When they do not, the event may last only a minute or less. This gives each eclipse a personality. Some are brief and dramatic. Some are low on the horizon. Some sweep across oceans. Some cross deserts with almost guaranteed clear skies. Some occur over populated regions and become shared cultural events. The mechanism is the same. The experience is not. A more typical totality lasts 2 to 3 minutes, and brief totalities near the edge of the path may be only a few seconds. The duration depends primarily on how close the eclipse path passes to the observer and on whether the moon is near its closest approach to Earth, at perigee, when the moon is largest and covers more of the sun, or near its farthest point, apogee, when the moon is smallest. This is why the exact centerline matters so much to eclipse observers. Being inside the path of totality is the essential thing, but being near the centerline usually gives a longer totality than standing near the edge. Near the edge, the sun may be completely covered for only a few seconds. At the centerline, under favorable geometry, the moon's shadow passes over you more fully and for longer. The difference can be the difference between a glimpse and an experience. This is also why a 99% partial eclipse is not almost the same as totality. It sounds almost the same numerically, but visually and emotionally it is a different category. 1% of the solar photosphere is still bright enough to keep the corona invisible and to keep the sky from becoming the strange twilight of totality. The final 1% is not a small detail. It is the difference between looking at a partly covered sun and standing in the moon's central shadow. People who have never seen totality sometimes underestimate this because numbers make the two experiences seem close. 98% sounds nearly complete. 99% sounds almost perfect. But eclipses are not experienced linearly. The last fragment of photosphere dominates everything. The sky, the air, the corona, the psychology of the crowd. All of these change only when the bright face of the sun is fully covered. Solar eclipses appear in human records stretching back to the earliest historical documents, and the story of humanity's attempts to understand, predict, and exploit them runs parallel to the development of astronomy itself. The earliest written records of solar eclipses come from ancient China. where astrologers were responsible for tracking celestial phenomena and reporting on their significance to the emperor. The earliest recorded eclipse in Chinese records is traditionally dated to 2136 BCE, though the reliability of extremely ancient Chinese astronomical records is debated by historians. More reliably documented Chinese eclipse records begin around the first millennium BCE and include systematic records maintained by court astronomers for whom eclipse prediction was a professional responsibility with serious political implications. Babylonian astronomers, perhaps the most systematic observers of the ancient world before the Greeks, developed the Saros cycle, a period of about 18 years, 11 days, and 8 hours after which eclipses repeat in a similar but not identical pattern. The discovery of the Saros, achieved by Babylonian astronomers through patient accumulation and comparison of eclipse records across many generations, was one of the most remarkable achievements of ancient science, a predictive tool of genuine accuracy derived entirely from observation and pattern recognition without any physical model of what was causing the eclipses. The Saros allowed Babylonian astronomers to predict when eclipses might occur, though not necessarily whether a specific one would be total or partial from a specific location, with a reliability that made their astronomical advice genuinely valuable to rulers concerned with celestial omens. The Greek philosopher Thales of Miletus reportedly predicted a solar eclipse that occurred during a battle between the Lydians and the Medes in approximately 585 BCE. The armies, so terrified by the sudden onset of darkness during the battle, immediately ceased fighting and negotiated a peace. Historians debate the precision of Thales's prediction. It is generally acknowledged that he could have used the Saros to predict that an eclipse was likely around that period, though whether the specific date and location could have been accurately predicted with ancient tools is uncertain. Whether or not the story is precise in its details, it captures something real about the relationship between eclipse prediction capability and power in the ancient world. The ability to predict a solar eclipse was genuinely impressive and genuinely useful in contexts where celestial omens had political significance. The ancient meaning of eclipses was not foolish in the simple way modern people sometimes imagine. Without a physical model of the solar system, the sudden disappearance of the sun was a real disturbance in the expected order of the world. If a society's calendar, rituals, agriculture, kingship, and theology were all tied to the sky, then an eclipse was not merely a shadow. It was a disruption of the public clock of existence. Prediction transformed that disruption. To know that an eclipse was coming did not necessarily remove fear, but it changed fear into authority. The person who could say when the sky would darken possessed a rare kind of power. This is one reason eclipse records are so valuable to historians and astronomers. They can anchor chronologies, help identify dates of ancient events, and even contribute to reconstructing long-term changes in Earth's rotation. The shadow of the moon, written down by someone thousands of years ago, can still carry information for modern science. The ancient Greeks made rapid progress in understanding the geometric principles behind eclipses. The Greek contribution was not simply that they rejected myth. It was that they turned the sky into geometry. Once an eclipse is understood geometrically, it becomes possible to use it as a measurement tool. The shape of Earth's shadow on the moon during lunar eclipses helped support the idea that Earth is spherical. Differences in eclipse visibility from different locations helped estimate distances. The timing and path of shadows tied astronomy to geography. An eclipse was no longer only an omen to interpret. It became a measuring instrument. Aristarchus of Samos, in the 3rd century BCE, used eclipse geometry to estimate the relative distances of the Sun and Moon from Earth, a remarkably sophisticated application of geometric reasoning that produced answers in the right ballpark even with the limited precision of observations available. Hipparchus, in the 2nd century BCE, used the geography of eclipse paths, specifically the fact that a particular eclipse was total at the Hellespont, but only partial at Alexandria, to determine the distance to the moon with surprising accuracy, arriving at a value within about 10% of the modern measurement. By the era of Ptolemy and later Islamic astronomy, eclipse prediction had become sophisticated enough to provide accurate advance warning not just of when an eclipse would occur, but of its magnitude, duration, and the limits of the zone of totality. Islamic astronomers preserved, criticized, and improved earlier astronomical traditions. They built observatories, refined tables, translated and corrected Greek works, and developed mathematical tools that helped predict celestial events with increasing accuracy. Eclipses were part of this broader program, not isolated curiosities. They mattered for calendars, astrology, religious timekeeping, and scientific understanding. The accumulated work later entered European astronomy through translations and scholarly exchange, becoming part of the long chain that eventually led to the precision celestial mechanics of the modern era. An eclipse prediction on a modern website may look instantaneous. Behind it stands thousands of years of recorded shadows. Medieval Islamic astronomers refined eclipse tables to a degree of precision that was not significantly improved until the development of Newtonian mechanics and the later mathematical machinery of celestial mechanics. Total solar eclipses have been the setting for several of the most significant scientific discoveries in history, two of which deserve particular attention: the discovery of helium and the confirmation of general relativity. Helium was first identified in sunlight during the total solar eclipse of August 18, 1868. The French astronomer Jules Janssen observed the eclipse from India and used a spectroscope, an instrument that splits light into its component wavelengths, to study the solar prominences and chromosphere. He saw a bright yellow spectral line that did not match any known element. Soon afterward, the English astronomer Joseph Norman Lockyer observed the same yellow line in the sun's spectrum without needing an eclipse, using spectroscopic techniques to isolate solar light. Lockyer and the chemist Edward Franklin proposed the name helium, after Helios, the Greek sun god, for what appeared to be an element present in the sun but not yet known on Earth. The possibility that there existed an element present in the sun but not on Earth was initially greeted with skepticism. The universe should, after all, be made of the same elements everywhere. This is one of the reasons the helium story matters so much. It showed that spectroscopy could turn light into chemistry. Before anyone held a sample of helium on Earth, a line in sunlight suggested that the element existed. The sun was no longer only a bright disk or a mythic object. It had a measurable composition. The same technique would become one of the foundations of astrophysics. Identify elements in stars, nebulae, galaxies, and distant worlds by reading the fingerprints in their light. A total eclipse helped reveal an element. The larger revolution was that the universe could be analyzed from afar. But helium was confirmed on Earth in 1895 when William Ramsay isolated it from the mineral clevite, and the spectral lines matched perfectly. Helium turned out to be the second most abundant element in the universe after hydrogen, present in enormous quantities on Earth as well, but too light to be retained by Earth's gravity and constantly escaping the atmosphere. Its presence in terrestrial minerals reflecting not an atmospheric inventory, but helium-4 produced by the radioactive alpha decay of heavier elements in the rocks. The element was real, it was on Earth, and it had been found first in the sun during a total eclipse. This discovery also changed the emotional relationship between Earth and the sun. The sun was no longer simply the source of light and warmth. It became a place with chemistry that could be read. The yellow line in the spectrum was a message, not in the poetic sense, but in the physical sense. Atoms in the sun were interacting with light in a way that could be measured on Earth. From that point forward, the stars were not unknowable fires. They were laboratories whose compositions could be studied from afar. That is one of the great turns in astronomy, from looking at the heavens to reading them. The confirmation of Einstein's general theory of relativity during the total solar eclipse of May 29, 1919, is one of the most celebrated events in the history of science. Einstein's 1915 theory made a specific prediction. Light passing near a massive body should be deflected from a straight path by the curvature of spacetime the mass creates. The amount of deflection predicted by general relativity was twice the value obtained from the older Newtonian-style calculation, a prediction that, if confirmed, would distinguish general relativity from Newtonian gravity in an experimentally accessible way. The total solar eclipse provided the experimental opportunity. During totality, stars near the sun's limb become visible, stars that are normally invisible because of the sun's overwhelming brightness, but that appear in the darkened sky of totality. If Einstein's prediction were correct, those stars should appear slightly displaced from their catalog positions because the sun's gravity is deflecting their light on its way to Earth. The apparent displacement is tiny, about 1.75 arcseconds at the sun's limb, decreasing with angular distance from the sun, but measurable with careful photography and precise astrometry. 2 expeditions were mounted to observe the 1919 eclipse, one led by Arthur Eddington to the island of Principe off the coast of West Africa, and one led by Andrew Crommelin and Charles Davidson to Sobral in Brazil. Both eclipse paths crossed regions accessible enough to reach, and both teams successfully observed the eclipse and photographed the stellar field around the sun during totality. Comparison of the eclipse photographs with photographs of the same star field taken at night 6 months earlier, when the sun was not near those stars, allowed measurement of any apparent displacement of the stellar positions. The results, announced at a joint meeting of the Royal Society and Royal Astronomical Society in London on November 6, 1919, confirmed Einstein's prediction. The public reaction was enormous because the results seemed to do something almost mythic. It showed that light itself could be bent. Of course, in modern physics the statement is more precise. Light follows the geometry of space-time, and mass changes that geometry. But for the public in 1919, the eclipse result meant that the old picture of space, time, gravity, and straight lines had shifted. The sun had briefly hidden itself so that stars near its edge could be photographed, and those stars appeared displaced in just the way Einstein had predicted. A shadow on Earth had tested the shape of spacetime. The measured deflection was consistent with general relativity's predicted 1.75 arcseconds and inconsistent with the Newtonian prediction of roughly half that value. Einstein's theory was confirmed by observation, and the announcement made front-page news worldwide. One of the rare occasions when a purely theoretical physics result became a global story. The headline in the Times of London declared, "Revolution in Science. New theory of the universe. Newtonian ideas overthrown." The 1919 eclipse confirmation has subsequently been refined by more precise measurements. Modern measurements of light deflection near the sun, using not visible light, but radio waves from quasars that happen to pass near the sun during the course of Earth's orbit, have confirmed the general relativistic prediction to better than 1 part in 10,000. Extraordinary precision that confirms Einstein's theory to a degree of accuracy far beyond what Eddington's expedition could achieve. But the 1919 eclipse holds its place in scientific history as the moment when a revolutionary theory of gravity moved from brilliant speculation to observational confirmation. It is worth remembering that the 1919 result was not the final proof of relativity in the modern precision sense. The observations were difficult. Weather, instrument issues, photographic plates, and the tiny size of the expected shift all made the measurement challenging. Later historians have examined the data and the analysis in detail. The result still stands historically as a real and important confirmation, but the confidence we now have in general relativity comes from many later tests: radio measurements, radar ranging, gravitational lensing, the orbit of Mercury, binary pulsars, gravitational waves, and the images and timing of black holes. The eclipse made Einstein famous. Later astronomy made the theory unavoidable. This is a useful lesson in how scientific fame works. Einstein did not become important because a newspaper headline said he was important. He became famous because a dramatic test arrived at exactly the right historical moment. A new theory, a visible cosmic event, an international expedition soon after a world war, and a result that could be explained to the public in a single stunning idea. Starlight bent around the sun. A total eclipse gave the theory a stage. And the stage mattered because totality made the impossible photographable. Without the moon covering the sun, the stars near the solar limb were lost in daylight. During totality, the sun became dark enough that those stars could be recorded. The eclipse did not create the bending of light. It created the conditions under which the bending could be measured. Sometimes science advances because nature briefly removes the glare. That distinction is important. Science rarely rests forever on a single dramatic observation. A single observation can open a door. A century of repeated tests tells us whether the door leads somewhere real. What do you actually see during a total solar eclipse? The experience unfolds over a period of time stretching from the first contact of the moon with the solar disk, the beginning of the partial phase, when the moon first begins to cover the sun, to the fourth and final contact when the moon fully clears the solar disk. The typical duration from first to fourth contact is about 2 to 3 hours, with totality itself lasting only minutes in the middle. For most of the partial phase, the eclipse seems surprisingly undramatic to the casual observer without the appropriate filters. This is one of the most counterintuitive parts of an eclipse. The sun is so bright that removing half of it does not feel like removing half the day. Human vision adjusts. The atmosphere scatters light. The ground remains illuminated. People who are not paying attention can live under a major partial eclipse and barely notice, especially if they are indoors or under thin cloud. But instruments notice. Light meters notice. Solar panels notice. Temperature sensors notice. The physics is changing steadily even before human perception fully catches up. This gap between measurement and feeling is part of the drama. For most of the partial phase, the mind can still treat the event as ordinary. Then, near totality, the compensation fails. The world changes too quickly and too strangely to ignore. The sun is still bright, still dangerous to look at directly, still illuminating the landscape in what appears to be normal daylight, despite a significant fraction of the disk being covered. The human eye and brain are extraordinarily adept at compensating for variation in illumination. We adapt to enormous ranges of light intensity without consciously noticing. A solar eclipse covering even 50 or 60% of the solar disk is not obviously different in ambient illumination from an ordinary cloudy day, and many people who have not been specifically looking for it have missed the early stages of significant eclipses entirely. The change becomes more obviously visible and more emotionally affecting as totality approaches, typically in the last 30 to 15 minutes before the moon completely covers the sun. This last phase has its own atmosphere. People check their watches. They check the sky. They compare the shrinking crescent through filters. Conversations shorten. Camera shutters begin. The crowd becomes aware that something irreversible is approaching. Even in a scientific gathering, even among people who can explain every step, there is often a visible change in mood. It is not panic. It is anticipation becoming physical. The moon's shadow, still unseen by many observers, is already close. The light begins to have a quality that is genuinely difficult to describe. Observers consistently reach for words like wrong, flat, gray, silver, eerie, otherworldly. The quality of shadow changes. Normal shadows, cast by a point source of light like the sun, have soft edges, but as the sun becomes a narrow crescent, the crescents of sunlight passing through the gaps between leaves in a tree or through the spaces in a mesh fence produce crescent-shaped patches of light rather than the usual circular spots. This is the pinhole camera effect. Each gap acts as a pinhole projecting a tiny image of the crescent sun onto the ground. The ground beneath trees becomes covered in crescent-shaped light patches, and this specific visual signature is one of the most reliably documented and widely reported phenomena of the partial eclipse phase. In the last minutes before totality, the pace of change accelerates. The light levels drop more noticeably. The temperature falls. The sudden removal of solar heating and the cooling radiative effect of the darkened sky can drop ambient temperatures by several degrees in a matter of minutes. Birds begin to roost. Insects may begin their evening sounds. Animals in general respond to the darkening as if an ordinary evening were approaching, accelerating through their late-day behaviors. Perhaps the most dramatic pre-totality phenomenon is the shadow bands, faint, rippling waves of light and dark that sweep across light-colored surfaces in the seconds immediately before and after totality, produced by the atmospheric refraction of light from the extremely thin crescent of the sun as it is distorted by turbulence in Earth's atmosphere. Shadow bands are especially strange because they seem almost alive. They are not shadows in the ordinary sense, not objects blocking light. They are interference-like patterns produced by the atmosphere acting on a thin solar crescent. They may appear on white sheets, walls, pavement, or pale ground, sliding rapidly in faint waves. Some observers miss them completely because they are looking upward. Others remember them as one of the most unsettling parts of the event because the ground itself seems to shimmer just before the sky changes. They are a reminder that an eclipse is not only an astronomical event, it is also an atmospheric one. Shadow bands are subtle and not visible at every eclipse. Atmospheric conditions affect their prominence, but when they appear, they seem to skitter and ripple across the ground in a way that has been described as similar to the patterns of light and shadow visible at the bottom of a shallow swimming pool. They are fleeting, lasting only seconds, and they are one of the more unusual and harder to photograph eclipse phenomena. In the final seconds before totality, the last remaining sliver of the solar disk, now perhaps only a tiny arc, breaks into a series of bright beads as sunlight shines through the mountains, valleys, and craters on the moon's limb. These Baily's beads, named after the English astronomer Francis Baily, who described them clearly in 1836, though they had been noted earlier, create a sparkling, jewel-like effect as the last points of photospheric light are extinguished one by one. The final Baily's bead, the last point of light from the photosphere, flares brilliantly just before totality begins, producing the diamond ring effect. A single bright point of photospheric light blazing at the edge of the darkened disk, surrounded by the full circle of the corona now becoming visible as the photosphere disappears. The diamond ring is one of the most photographed eclipse moments, but it is not the safest moment to stare at without protection. It is still photospheric light. It is beautiful because a last intense point of the sun is visible. That also means it is bright. Experienced observers know that the truly safe naked eye interval begins only when that photospheric bead is gone and totality has fully begun. Then, for a brief time, the corona is visible directly. The return of the diamond ring means totality has ended and protection must return. The emotional climax therefore sits right beside the practical boundary. The same flash that announces wonder also announces danger if watched carelessly. The diamond ring lasts only a second or two, and then it is gone, and totality begins. The corona appears. The corona is the sun's outer atmosphere, extending millions of kilometers into space from the visible solar surface. And it is visible during totality because the photosphere, which normally outshines it by a factor of roughly 1,000,000, has been completely blocked by the moon. The corona is also the beginning of the solar wind. The plasma that streams outward from the sun into interplanetary space does not begin as something separate from the corona. It is an extension of the sun's outer atmosphere, guided and shaped by magnetic fields, accelerated outward until it flows past the planets and fills the heliosphere. Every planet, including Earth, lives inside this extended solar environment. Auroras, geomagnetic storms, satellite disruptions, and the boundary of interstellar space are all connected to the same solar wind whose roots lie in the corona. During totality, then, the viewer is seeing not merely a halo but the visible base of a system that reaches beyond Pluto and into the outer heliosphere. That is a large thing to see with the naked eye. What you see is a glowing, white, structured halo extending outward from the dark disk of the moon, with streamers and plumes and complex filamentary structure reaching outward in ways that change measurably from eclipse to eclipse, depending on where the sun is in its 11-year activity cycle. Near solar minimum, the corona shows long, sweeping equatorial streamers with relatively little structure at the poles. Near solar maximum, it is more symmetrical and complex, with structure visible in all directions. The color of the corona is white, not the yellow or orange of sunset light, not the pale gold of some artistic depictions, but genuinely white, the unmixed light of the photosphere scattered by the electrons of the coronal plasma. Beside the white corona, on some eclipses, the pink rim of the chromosphere is visible at the moon's edge, and rising from the chromosphere like colored flames, the prominences, enormous arcs of plasma reaching heights of tens of thousands to hundreds of thousands of kilometers above the solar surface. Following the lines of the sun's magnetic field, glowing in the deep red of hydrogen alpha emission. The sky itself, during totality, is dark enough to show the brighter planets and the brightest stars. How dark depends on how deep in the umbra you are and on how close to solar maximum the eclipse occurs. A corona at solar maximum is somewhat brighter than at minimum. Typically, the sky during totality is comparable to civil twilight, dark enough to see planets and first magnitude stars, but not the densely packed stars of a dark sky night. Venus is nearly always visible during totality if it is anywhere near the sun's vicinity. Jupiter, Saturn, and bright stars like Sirius or Regulus can often be seen as well. This appearance of stars and planets in a blue gradient sky, simultaneously dark enough to show stars and bright enough to see the horizon, is one of the visually unique aspects of totality, a sky that looks like nothing that exists outside the path of a total solar eclipse. The horizon is part of the strangeness. During totality, the sky above may be dark, but the horizon can glow in every direction because places outside the umbra are still in daylight. You are standing inside a moving island of shadow, surrounded by distant sunlight. This is not the same as night, when half the planet is turned away from the sun. It is a local darkness imposed on the day. That is why the eclipse can feel spatial as well as visual. The darkness has edges. It is a shape on Earth. If you could rise high enough, you could see the moon's shadow as a dark spot moving across the planet. From the ground, you sense that geometry through the ring of light around the horizon. And then, in 2 to 7 minutes, or 20 seconds, or 10 seconds, if you are near the edge of the path, it ends. The ending is almost shocking. The return of direct sunlight feels faster than the disappearance. The world snaps back. The corona vanishes into brightness. The planets fade. the horizon loses its strange glow. The crowd may cheer, laugh, or simply stand in silence. And for a few minutes afterward, ordinary daylight feels almost too ordinary. The same sun that was hidden moments earlier becomes impossible to look at again. This return is part of the emotional effect. Totality does not gradually dissolve. It is taken away. A new diamond ring appears on the opposite limb of the moon. Baily's beads return briefly, and the photosphere begins to reappear. The corona vanishes, the sky returns to blue, the temperature begins to rise, the birds and insects stop their evening behaviors and resume their daytime ones, and the world is ordinary again. People in the path of totality often describe the immediate aftermath as a kind of stunned silence, followed by applause, laughter, or tears, frequently all three. Those who have seen totality before begin immediately planning when and where they can see it again. There is one practical truth that belongs inside the beauty of the event. A solar eclipse is still the sun. During the partial phases before and after totality, and during any annular or partial eclipse, direct viewing requires proper solar protection. Ordinary sunglasses are not safe. Eclipse glasses or handheld viewers should comply with the ISO 12312 2 standard, and cameras, binoculars, and telescopes require their own special solar filters placed over the front of the optics, not simply eclipse glasses held near the eyepiece. The only brief exception is the total phase of a total solar eclipse, when the bright photosphere is completely covered by the moon. That is when the corona can be viewed directly. The moment the first bright bead of sunlight returns, protection is required again. This safety rule does not make the event less magical. It makes it observable. The scientific study of the solar eclipse has generated important advances beyond the two dramatic moments of helium discovery and general relativity confirmation. The eclipse has served as a recurring laboratory for solar physics throughout the telescope era. The chromosphere, the layer of the solar atmosphere immediately above the photosphere, is visible during the brief seconds of Baily's beads and during the first and last seconds of totality when the thin red rim is exposed before the corona overwhelms it. The chromosphere is easy to miss because it appears for so little time. The word means color sphere, and during an eclipse it can appear as a thin, reddish arc along the moon's edge. Its light is dominated by emission from hydrogen, especially the deep red hydrogen alpha line. Prominences rising from it can look like small red flames, though they are not flames in the ordinary chemical sense. They are enormous structures of plasma guided by magnetic fields, sometimes larger than Earth many times over. This is another moment when scale becomes deceptive. A tiny red feature at the edge of the moon can be a loop of plasma tens or hundreds of thousands of kilometers high. The eye sees a small detail. The mind, if it knows what it is looking at, sees a structure large enough to swallow planets. Spectroscopic observations of the chromosphere during eclipses, beginning in the 19th century, revealed a distinctive flash spectrum, the emission line spectrum of the chromospheric gases appearing for only a few seconds on either side of totality, replacing the absorption line spectrum of the photosphere with a complementary set of bright emission lines from the same elements. The analysis of these flash spectra was essential to early understanding of the chromosphere's composition and physical state. The corona structure, imaged in detail from eclipse to eclipse, provides information about the sun's magnetic field configuration and the sources of the solar wind. Coronal streamers, the elongated structures that extend hundreds of solar radii into space along magnetic field lines, are most easily photographed during total eclipses, and their changing configuration over the solar cycle reveals the changing topology of the sun's magnetic field. Before coronagraphs, instruments that create an artificial eclipse by blocking the solar disk were developed in 1930 by Bernard Lyot, total solar eclipses were the only means of observing the corona at all. Even after coronagraphs became available, the artificial eclipse they create cannot fully replicate the natural eclipse, because the coronagraph's occulting disk also blocks the inner corona, limiting access to coronal structure closest to the solar limb. The study of the corona's composition and temperature during eclipses contributed to some of the early evidence for the coronal heating mystery, the surprising discovery that the corona is hundreds of times hotter than the photosphere below it, a phenomenon that violates simple intuition about heat flow and that remains a subject of active research as discussed in the Sun episode. The coronal heating mystery is one of the reasons eclipses remain scientifically relevant even in the space age. We now have spacecraft that watch the sun continuously. We have coronagraphs that block the disk artificially. We have ultraviolet and X-ray telescopes that see hot plasma directly. Yet total eclipses still offer a uniquely clean view of the inner and middle corona in visible and near-infrared light. The moon's edge is sharper and more distant than the occulting disk inside an instrument, and the natural eclipse can reveal structures close to the solar limb that artificial coronagraphs may partly obscure. This does not mean eclipses are the only way to study the corona anymore. They are not, but they remain a special laboratory, brief, demanding, and valuable, especially when coordinated observations are taken from many locations along the path. Spectroscopic observations of the corona during eclipses identified emission lines from highly ionized iron atoms with 13 or more electrons stripped away, that implied coronal temperatures of millions of degrees, a measurement that was initially disbelieved when first reported because temperatures that extreme seemed physically implausible for an atmosphere above a surface of only 6,000 degrees. Solar eclipses have also been used to study Earth's upper atmosphere. This connection between eclipse and atmosphere is often overlooked. A total eclipse is caused by bodies in space, but it is experienced through Earth's air. The cooling at the surface depends on local weather, humidity, wind, land type, and cloud cover. The darkness depends on scattering in the atmosphere. Shadow bands depend on atmospheric turbulence. The ionosphere responds to the sudden change in solar radiation. Even the color of the horizon during totality is an atmospheric effect shaped by sunlight outside the umbra. So the eclipse is not only the moon covering the sun, it is the whole Earth system responding briefly to the moving shadow. The sudden withdrawal of solar ultraviolet and X-ray radiation during an eclipse produces rapid changes in the ionosphere, the layer of ionized gas in the upper atmosphere that reflects radio waves and enables long-distance radio communication. Systematic measurements of radio propagation during eclipses have provided information about the ionosphere's response to solar radiation that is complementary to direct instrument measurements, and the detailed study of ionospheric eclipse effects has contributed to our understanding of how Earth's atmosphere couples to the solar radiation environment. Modern eclipse science often combines professional instruments with citizen science. Temperature sensors can record the cooling at the surface. Radio operators can measure changes in propagation as the ionosphere responds to the sudden loss of solar radiation. Cameras spread along the path can image the corona from different locations, extending the effective observing time as the shadow moves. Observers can record animal behavior, cloud changes, shadow bands, and local atmospheric effects. A total eclipse is brief at one site, but across a continent or ocean, it is a moving experiment. This is one of the beautiful modern changes in eclipse science. Ancient observers recorded an omen. 19th-century astronomers carried spectroscopes and photographic plates into the path. Today, a total eclipse can become a distributed scientific campaign involving spacecraft, aircraft, observatories, schools, radio amateurs, photographers, and people standing in fields with small instruments. The moon's shadow becomes a temporary research platform. That platform also creates a rare collaboration between professionals and ordinary observers. A single person with eclipse glasses and a notebook is not replacing a solar observatory, but many people recording temperature drops, animal behavior, cloud changes, sky brightness, or radio effects can contribute to a wider picture. This is one of the rare astronomical events where public experience and scientific measurement naturally overlap. The same few minutes that make people cry can also produce data. This combination helps the episode avoid becoming passive. The viewer is not only being told about a distant phenomenon, they are being shown something they may one day safely observe, record, and understand for themselves. That platform is moving, and that is both the difficulty and the opportunity. If observers are spread along the path, each group sees totality at a different time. Combined, they can follow changes in the corona over a longer interval than one side allows. Aircraft can extend observations by moving with the shadow. Balloons can rise above some of the lower atmosphere. Satellites can provide context from space. The result is not one observation, but a choreography of observations tied to a shadow moving across Earth. The eclipse lasts minutes locally, but scientifically it can become a moving sequence. The Saros cycle, the period of 18 years, 11 days, and 8 hours after which the Sun, Moon, and Earth return to nearly the same relative geometry, is one of the most elegant results in celestial mechanics, and understanding it properly illuminates the structure of the eclipse prediction problem. The Saros is approximately 223 synodic months, the unit of time in which the moon returns to the same phase. The elegance of the Saros is that it is not based on one cycle, but on the near agreement of several cycles. A new moon alone is not enough. The moon also has to be near a node. And the moon's distance matters because its apparent size determines whether the eclipse is total, annular, or hybrid. The Saros works because the phase cycle, the node cycle, and the distance cycle nearly line up after about 18 years and 11 days. The word nearly matters. If the alignment were exact, eclipses would repeat perfectly. Because it is not exact, each Saros series evolves slowly across centuries. This is a beautiful example of prediction without perfection. The sky gives patterns, but the patterns breathe. It is also approximately 239 animalistic months, the unit in which the moon returns to the same point in its elliptical orbit, relevant because the moon's apparent size changes depending on whether it is at perigee or apogee. And it is approximately 242 draconic months, the unit in which the moon returns to the same node, the crossing point of the moon's orbit and the ecliptic, essential for any eclipse to occur. The near coincidence of these three different cycles over the 18-year Saros period means that after one Saros, the Sun-Moon-Earth geometry is very nearly the same, and an eclipse of very similar character recurs. The same type of eclipse, total, partial, annular, occurs at roughly the same time of year for roughly the same duration. This makes the Saros an excellent long-period predictor of eclipses. The qualifier nearly is important. The Saros is not perfect. The additional 8 hours in the cycle, the fractional day, means that the eclipse recurs when Earth has rotated about 120 degrees from the previous position. An eclipse visible from one hemisphere will, one Saros later, be visible from about 120 degrees of longitude further west. And the small mismatches between the three cycles mean that successive Saros eclipses are slightly different in character. The shadow may track somewhat northward or southward from one Saros to the next. A series of eclipses related by successive Saros periods is called a Saros series, and each series lasts about 12 to 13 centuries, encompassing about 60 to 80 individual eclipses as the shadow path gradually drifts from polar to equatorial regions and then off the Earth entirely. Grouping eclipses by Saros series is a natural way to understand eclipse patterns. The August 21st, 2017 eclipse that crossed the continental United States, the first total solar eclipse to trace a path entirely across the contiguous U.S. since 1918, belonged to Saros 145. Saros families also give eclipses a kind of genealogy. An eclipse is not an isolated event. It belongs to a family that began as a small partial eclipse near one pole, grew through central eclipses over many centuries, and will eventually fade into partial eclipses near the opposite pole. Each eclipse in the family resembles its predecessor, shifted in longitude and slightly changed in latitude and duration. The family has a birth, maturity, and death measured not in years, but in more than 1,000 years. This is one of the quiet pleasures of eclipse astronomy. Even the briefest event belongs to a long lineage. One Saros later, on September 2, 2035, a similar eclipse will occur, visible from approximately 120 degrees of longitude to the west. 3 Saros periods later, in 2063, the series will produce an eclipse visible from a different region again. The April 8, 2024 total solar eclipse that crossed Mexico, the United States, and Canada, one of the most widely observed eclipses in modern history, belonged to Saros 139 and will repeat 18 years and 11 days later over different geography. The practical use of the Saros was known to the Babylonian astronomers, who accumulated eclipse records over many generations precisely because the long Saros period means that useful experience accumulates slowly. If one person's observational career spans 30 or 40 years, they can at most witness 2 complete Saros cycles. This long timescale is important. Human memory alone is not enough for the Saros. The pattern is longer than a childhood, longer than a political reign, longer than many working lives. To discover it, a culture needs record keeping. It needs institutions. It needs people who believe observations are worth preserving for someone who will not be born until after the observer is dead. In that sense, eclipse prediction is also a story about civilization. The sky repeats slowly enough that only a society capable of transmitting memory can learn the pattern. Only by systematically recording and transmitting observations across generations could the pattern emerge. The Babylonian eclipse records, maintained as part of a broader program of celestial observation in service of astrological prediction, accumulated the data across many generations that made the Saros recognizable as a pattern. A different approach was apparently used by the builders of the structures at Stonehenge in Wiltshire, England, though the astronomical purpose of Stonehenge remains debated by archaeologists. The outer ring of 56 pits at Stonehenge, called the Aubrey holes, can be used as a calculator of eclipse possibility if a marker is moved by 2 or 3 holes per year, tracking the nodal cycle and indicating when eclipses are possible. Whether this was actually how the holes were used, whether Neolithic peoples in Britain were sophisticated enough in their astronomical observations to have identified the nodal cycle and to use a physical counting device to track it, is a matter of debate. But the physical possibility that Stonehenge could function as an eclipse predictor has been demonstrated mathematically, and it is consistent with what is known of the astronomical sophistication of late Neolithic cultures. This is a good place to be careful. Stonehenge is sometimes described too confidently as an eclipse computer, but the archaeological evidence is more complicated. The monument clearly has solar alignments, especially connected to solstice sunrise and sunset. Whether the Aubrey holes were actually used to predict eclipses is debated. The mathematical possibility is interesting, but possibility is not proof of use. That caution makes the story stronger rather than weaker. Ancient astronomy was real. Ancient people watched the sky closely. But we should not turn every ancient monument into a machine simply because a modern calculation can be fitted to it. The path of totality of the April 8th, 2024 total solar eclipse crossed North America in a diagonal path from the Pacific coast of Mexico through Texas, the Midwestern United States, New England, and the maritime provinces of Canada, a path that put totality within reach of tens of millions of people and attracted eclipse chasers from around the world. The 2024 eclipse occurred near solar maximum. The sun was at or near its peak activity level in the current solar cycle, meaning the corona was expected to be particularly extensive and complex compared to eclipses near solar minimum. Solar maximum and solar minimum give eclipse observers two different faces of the sun near minimum. The corona often stretches outward in long equatorial streamers, more flattened and orderly. Near maximum, magnetic activity appears across more latitudes, and the corona can look fuller, rounder, more chaotic. Prominences may be more numerous or more dramatic. The difference does not require a telescope to sense, especially in photographs, but understanding it gives the view more meaning. The corona is not a fixed crown. It is a changing atmosphere. This is why eclipse photographs from different years can look so different. Some coronas stretch sideways in long, elegant streamers. Some form a rounder halo. Some show delicate polar plumes. Some are dominated by large helmet streamers or bright structures connected to active regions. The moon covers the same photosphere, but the solar atmosphere exposed around it is never exactly the same. A person chasing eclipses is not only repeating an experience. They are watching different states of the sun. This expectation was borne out. Observers along the path reported an unusually active-looking corona with structure visible in all directions, along with multiple solar prominences visible with the naked eye as red features at the moon's limb, a vivid and colorful display compared to the more subdued corona of a minimum eclipse. The 2024 eclipse was among the most widely observed in history, reflecting both the high population density along the path of totality and the reach of modern media and social communication. The 2024 eclipse also arrived at a particularly active moment in the solar cycle. Near solar maximum, the sun's magnetic field is more complex. Sunspots are more common. Prominences may be more dramatic, and the corona tends to appear fuller and less flattened than it does near solar minimum. This does not make every solar maximum eclipse automatically better, but it changes the shape of what observers see. The corona becomes a record of the sun's magnetic mood at that point in its 11-year cycle. This is one reason people who see many eclipses do not simply repeat the same experience. The geometry repeats. The sun does not. Every totality shows a different corona. Live streams were broadcast from multiple locations along the path. NASA and various universities conducted scientific observations from aircraft, balloons, and ground stations distributed across the path. The ionospheric effects of the eclipse were studied by a distributed network of amateur and professional radio operators. Multiple citizen science programs enrolled hundreds of thousands of participants to make coordinated measurements of temperature, animal behavior, atmospheric phenomena, and other eclipse effects. The sociological aspect of modern eclipse viewing is itself remarkable. This modern sociological aspect also includes public safety. A total eclipse brings together people who may never have used eclipse glasses before, who may be tempted to look too early or too late, or who may assume that a phone camera, sunglasses, smoke glass, or a dark filter is enough. It is not. Safety has become part of eclipse culture because the event invites attention to the sun at exactly the time when people are most emotionally excited. The safest public guidance is simple. Use proper solar viewers for every partial phase. Remove them only during totality if you are in the path and the sun is fully covered. Put them back on immediately when the bright photosphere returns. The rule is simple because the moment is intense. This matters for an audience because many listeners may one day try to watch an eclipse themselves. The script should give wonder, but it should also quietly give the right habit. In the months before a major total solar eclipse, the population of towns along the path of totality swells dramatically as eclipse chasers, tourists, and scientists arrive in advance of the event. Hotels fill months in advance. Traffic can be severe on eclipse day, as people realize the night before that they need to position themselves within the path. The meteorological risk, that cloud cover will block the view, adds an element of tension to eclipse planning that can require last-minute decisions about whether to drive to a clearer location. The community of experienced eclipse chasers, people who have seen totality many times and who plan their lives around upcoming eclipse opportunities, is a distinctive subculture with its own vocabulary, traditions, and expertise. What motivates eclipse chasers? The answer, as documented in conversations with people who have pursued totalities to remote locations on multiple continents, is almost always the same. Having seen one total eclipse and found the experience larger than anything they had anticipated, they need to see another. There is another reason eclipse chasing becomes compelling. Every eclipse includes risk, not danger, necessarily, though travel can be difficult. Risk in the sense of uncertainty. You can choose the correct country, the correct city, the correct road, the correct centerline, and still lose the eclipse to one cloud at the wrong minute. You can plan for years and make the final decision in an hour based on satellite weather images. The event is deterministic in the sky, but uncertain on the ground. That combination is powerful. Celestial mechanics promises the shadow. Weather decides whether you see it. This is why eclipse observers often remember not only the moment of totality, but the whole day around it. The drive before dawn, the anxiety over cloud cover, the sudden clearing, the crowd's mood, the silence before totality, the impossible speed with which the minutes pass. The experience is described as addictive in a way that other natural spectacles are not. A beautiful sunset can be seen from home many times. A brilliant meteor shower happens every year. But a total solar eclipse occurs at any given location roughly once in 3 or 4 centuries. And the experience of totality, the corona, the diamond ring, the darkened sky, the silence or applause, the sudden visceral understanding of the orbital geometry of the solar system, is something that resists full re-experience in memory and demands to be repeated in person. Some people have seen 20, 30, or 40 total solar eclipses, traveling to Indonesia, to the Sahara, to Siberia, to the mid-Pacific, to wherever the moon's shadow is scheduled to fall. These veterans of eclipse chasing speak about their accumulated experiences in ways that combine the scientific and the aesthetic with an almost personal relationship with the phenomenon, an ongoing conversation with the celestial mechanics that delivers totality to different points on the globe in a pattern that rewards study and preparation with the opportunity to stand, again, in the darkened shadow of the moon. Beyond the total solar eclipse and its dramatic properties, the broader family of eclipse types encompasses several related phenomena worth understanding. Annular eclipses occur when the moon is near apogee, its farthest point from Earth, and therefore appears slightly smaller than the sun in angular size. The moon's disk is not large enough to fully cover the sun, and at the moment of annularity, the central phase of the annular eclipse, a ring or annulus of the sun's photosphere, remains visible around the moon's silhouette. Annular eclipses are visually striking in a different way from total eclipses. The landscape remains surprisingly bright. The ring of sunlight is dazzling, and there is no corona visible. The absence of the corona is the key difference. An annular eclipse may look spectacular through proper filters, with a bright ring surrounding the dark moon. But because some of the photosphere remains visible at all times, the sky does not fall into true eclipse darkness. The corona remains hidden. The emotional and scientific character is therefore different. Annularity is beautiful, but it is not totality. This is why eclipse observers can be so insistent about the distinction. They are not being dramatic. The physics genuinely changes at totality. But annular eclipses require exactly the same alignment conditions as total eclipses and follow the same prediction rules. Whether an eclipse is total or annular depends on whether the moon happens to be near perigee or apogee at the time. Hybrid eclipses, sometimes called annular total eclipses, occur when the moon is at almost exactly the right distance to produce total coverage. Because Earth is a sphere, the curvature of the Earth's surface means that different points along the path of a hybrid eclipse may be slightly different distances from the moon, and the eclipse can be total at some points along the path, where the Earth's surface curves closer to the moon, and annular at others, where the curvature moves the surface slightly farther away. Hybrid eclipses are relatively rare, about 5% of all central eclipses, and produce a particularly complex observational situation. Hybrid eclipses are a reminder that the labels total and annular are not always separated by much. Sometimes the tip of the moon's umbra barely reaches Earth. Along one part of the path, the curvature of Earth brings the surface close enough to enter totality. Along another part, the surface lies just beyond the umbral tip, and the eclipse is annular. In those cases, the difference between seeing the corona and seeing a ring of photosphere is a matter of geometry measured on a planetary curve. The observer's location does not simply select a view. It participates in the geometry. Partial solar eclipses are the most common type experienced from any given location because the penumbra, the region of partial shadow, is much larger than the umbra, covering a much wider swathe of Earth. During a partial eclipse, the moon covers some fraction of the solar disk but never completely covers it. Partial eclipses are worth observing safely with appropriate filters but lack the dramatic corona, the diamond ring, the rapid darkening, and the emotional impact of totality. Many people who have experienced a large partial eclipse and then experienced a total eclipse describe them as essentially different phenomena. The partial eclipse as an interesting astronomical event, the total as something categorically different in its effect. That distinction is important for people planning their first eclipse. If the path of totality is a few hours away, the difference is worth the travel. Staying outside the path for a 97 or 99% partial eclipse may sound practical, but it means missing the central phenomenon. You will see the sun partly covered, and the light may become strange, but you will not see the corona with your unaided eye. You will not stand inside the umbra. You will not experience the sudden switch from partial eclipse to totality. The path is narrow because the event is rare in exactly that way. For someone deciding whether to travel, this is the practical truth of the entire episode. A partial eclipse can be seen across a vast region. Totality belongs to a narrow stripe. The difference between those two regions can be a few kilometers, one wrong motorway exit, one choice of town instead of another. That sharpness feels almost unreasonable until you remember what is happening. A small lunar shadow cone is touching a rotating planet. The experience is not distributed evenly. It is drawn as a line across Earth. Solar eclipses on other planets are a different matter entirely, and the variety of eclipse phenomena available elsewhere in the solar system reflects the enormous diversity of moon-planet-sun geometries. Earth's eclipse is therefore part of a much wider family of shadow events. Every moon that passes between its planet and the sun creates a version of the same geometry. Every planet that casts a shadow on a moon creates another. But Earth's total solar eclipse has a particular balance that makes it unusual for observers on the ground. The moon is close enough in apparent size to hide the photosphere, but not so large that it erases the dramatic view of the corona and chromosphere. It is a near-perfect occulting disk made by nature. This is why solar eclipses on Mars, beautiful as they are, do not have the same character. Phobos crosses the Sun quickly as an irregular dark silhouette. It is a transit, not a true totality. Jupiter's moons can cast deep shadows on the planet, but there is no stable surface where a person could stand and watch the event in the same way. On Earth, the geometry, the surface, the atmosphere, and the human observer all meet. Jupiter's 4 Galilean moons cast shadows on Jupiter that are readily visible through Earth-based telescopes. The circular shadow of Io, Europa, Ganymede, or Callisto crossing Jupiter's cloud tops appears as a small dark circle moving across the planet. From the surface of Jupiter, hypothetically, ignoring the impossibility of a solid surface to stand on, the eclipses produced by these moons would be nothing like Earth's, because the moons subtend very different angular sizes from Jupiter's cloud tops than the moon does from Earth. Io, the closest Galilean moon, would appear far larger than the Sun from Jupiter, producing total eclipses that completely cover the Sun with a large dark disk. Ganymede, the farthest of the 4, subtends roughly the same angle as the Sun from Jupiter, producing eclipses vaguely reminiscent of Earth's. Mars has 2 tiny moons, Phobos and Deimos, both far smaller than Earth's moon and both appearing much smaller in Mars's sky than the Sun. The Martian examples are especially useful because we have seen them from the ground. Rovers on Mars have photographed Phobos and Deimos crossing the Sun. The images are haunting because they show an eclipse from another world, but they also reveal how different that world is. Phobos is irregular, close, fast, and too small to cover the Sun. Its transit is a dark bite moving across the solar disk. Deimos is even smaller. The result is scientifically valuable and visually strange, but it does not produce the transformation of landscape and sky that a total eclipse produces on Earth. The comparison makes Earth's eclipse feel even more specific. When Phobos or Deimos transits the Sun as seen from Mars, they produce what amounts to a partial eclipse, a small dark dot moving across the solar disk, rather than anything approaching totality. The Mars rover's Spirit, Opportunity, Curiosity, and Perseverance have all photographed transits of Phobos and Deimos across the Sun from Mars's surface, producing unusual and beautiful images that show the irregularly shaped moons as small silhouettes against the solar disk. Saturn's numerous moons produce a range of eclipse phenomena, from the shadows of the large moons Titan and Rhea casting clearly visible circles on Saturn's cloud tops, visible from Earth through moderate telescopes during favorable geometry, to the extraordinary circumstance of watching Saturn's shadow fall on its rings during certain orbital configurations. The ring shadow and the satellite shadows create complex patterns of light and dark during the northern or southern winter of Saturn, when the rings are edge onto the Sun and cast their shadow across the planet in a wide band. From the surface of Europa, if you could stand on its icy surface, Jupiter would appear about 11 times larger in diameter than the Sun, producing regular total eclipses when Jupiter's shadow falls on Europa that would completely blot out the Sun and cover it with the enormous disk of Jupiter, the planet's banded atmosphere potentially visible in detail. The future of total solar eclipses on Earth is finite but not immediately threatened. This future loss is not something to mourn in an immediate practical sense. Hundreds of millions of years is longer than the existence of our species, longer than the rise and fall of mountain ranges, longer than the current arrangement of the continents. But astronomy often asks us to think in timescales where even that becomes a chapter. The eclipse window has a beginning and an end. In the distant past, eclipses were different because the moon was larger in the sky. In the distant future, they will be different because the moon will be smaller. The present era is not permanent. It is an interval. The moon's recession of about 3.8 centimeters per year is slow enough that total solar eclipses will continue for hundreds of millions of years. The recession of the moon is not a guess based only on theory. It is measured directly. Laser ranging experiments, using retroreflectors left on the lunar surface by Apollo astronauts and later lunar missions, allow scientists to measure the Earth-Moon distance with extraordinary precision. The moon is moving away because tides raised on Earth by the moon do not point exactly at the moon. Earth's rotation carries the tidal bulge slightly ahead, and the gravitational interaction transfers angular momentum from Earth's spin to the moon's orbit. Earth rotates a little more slowly over time, and the moon moves a little farther away. This tidal exchange is slow by human standards and immense by geological standards. It lengthens the day, changes the moon's orbit, and gradually alters the eclipse geometry. The total solar eclipse is therefore connected to tides, the slowing rotation of Earth, and the long dynamical history of the Earth-Moon system. The same moon that raises the oceans is also moving toward a future where it will no longer fully cover the sun. This connects eclipses to one of the oldest rhythms humans have known. The moon shapes tides, months, calendars, migration patterns, coastal ecosystems, mythology, navigation, and human timekeeping. A total eclipse is not separate from that larger lunar influence. It is one of the rare moments when the moon's relationship with Earth and Sun becomes impossible to ignore. The familiar object of the night sky becomes a precise dark instrument in daylight. The moon is usually gentle in the way it enters human life. Phases, tides, pale light, months. During a total solar eclipse, it becomes absolute. The exact final date depends on the details of the Earth-Moon orbit and the changing apparent size of the sun, but the broad conclusion is clear. One day the moon will appear too small to cover the sun's disk from anywhere on Earth's surface. After that, annular eclipses will still occur, but total eclipses, with their corona, their diamond ring, their momentary darkening of the sky, will no longer be possible. In the near future, the next several decades bring a number of noteworthy total eclipses for various continents. For a channel called Space for Sleep, future eclipses are useful because they connect the cosmic to the practical. A viewer may never visit Pluto, see a black hole, or stand on the surface of Mars. But a total solar eclipse is something a person can actually plan to experience. The path is narrow, but it is on Earth. It crosses roads, hotels, farms, beaches, deserts, towns, and cities. It belongs to orbital mechanics, but also to weather apps, train tickets, school calendars, and traffic. That closeness makes the subject unusually powerful. It is space science that can arrive on a human schedule. On August 12, 2026, a total solar eclipse will sweep across Greenland, Iceland, the Atlantic Ocean, Spain, and a small corner of Portugal. For Spain, this eclipse is especially important. The path of totality crosses the country near sunset, making clear western horizons and local weather unusually important parts of the viewing plan. The 2026 eclipse over Spain deserves special attention because it is not only a future astronomical event, it is a near-future cultural event. For much of Europe, totality is often something that requires serious travel, another continent, an ocean crossing, a remote desert, a ship, a long-planned expedition. In 2026, the path comes directly across part of Europe, and Spain becomes one of the central places where ordinary people can experience totality without traveling halfway around the world. But it will not be a simple overhead eclipse. In Spain, the sun will be low. That means the view will be sensitive to local horizon conditions. A ridge, apartment block, coastal haze, mountain line, or even a poorly chosen valley could matter. The low sun may make the eclipse visually beautiful, with the corona close to the horizon and the landscape illuminated from a shallow angle. but it also makes planning less forgiving. For the script, this is useful because it brings the subject close to the viewer. A total solar eclipse is not only something from ancient China, India, Brazil, or a NASA map. It is something with dates and places already approaching. The moon's shadow is not abstract. It has appointments. On August 2nd, 2027, another total solar eclipse will cross the Strait of Gibraltar, North Africa, Egypt, the Arabian Peninsula, and parts of the Indian Ocean region. Near Luxor, Egypt, totality will last about 6 minutes and 22 seconds, making it one of the longest and most scientifically attractive eclipses of the century. The 2027 eclipse has almost the opposite personality. It is not low and brief in the same way. It is long, bright, and desert-favored. Near Luxor, the combination of long duration and generally favorable weather prospects makes it one of the great eclipse targets of the 21st century. 6 minutes and 22 seconds is enough time for scientific instruments to collect richer data and enough time for human observers to move past the first shock into a more sustained awareness of the corona. Long totalities are not just longer versions of short totalities. They change what can be noticed. In a short eclipse, the mind may register the diamond ring, the corona, the planets, the horizon, and the return of light almost as one overwhelming event. In a long eclipse, the eye can travel around the corona, look at prominences, find planets, look down at the landscape, look back up, and still have time left. That is why eclipse chasers are already thinking about it. Australia will see a major total solar eclipse in July 2028. North America will receive another important total eclipse in August 2044. Planning for these future eclipses begins years, and in some cases decades in advance among the eclipse-chasing community, and the logistical preparation, ensuring clear skies, accessible locations, adequate transportation, becomes more elaborate as the eclipse approaches. The planning is part of the culture. Experienced eclipse chasers study cloud climatology, road networks, elevation, local terrain, political stability, mobility on eclipse day, and backup routes. They learn that the synaline is not always the best place if the synaline is likely to be cloudy. They learn that a shorter totality under clear sky is better than a longer totality under cloud. They learn to prepare equipment, but not become so obsessed with equipment that they forget to look. The simplest advice from experienced observers is often the best. During your first totality, look with your eyes. Take a few photographs if you must, but do not spend the whole event behind a camera. The eclipse is short. Memory matters. That advice sounds simple, but it is hard to follow. When totality begins, the instinct is to do everything at once. Photograph the corona, look for Venus, check the horizon, listen to the crowd, inspect prominences, remember safety, and somehow feel the experience fully. There is never enough time. Even a long eclipse feels brief. The mind tries to hold too many things, and the event moves on. That is another reason people chase the next one. They want another chance to look properly, even though the next one will also be too short. The meteorological challenge of eclipse planning is one of its more practically demanding aspects. Cloud cover can render an eclipse completely invisible from a ground location, and the decision about whether to stay at a prepared site or to drive hours in hopes of clearer skies is one that eclipse observers face with imperfect information and real-time pressure. There is also the ordinary but essential matter of preparation. Certified eclipse glasses, spare glasses, a clear horizon when the eclipse is low, a backup location if clouds move in, and a plan for traffic after totality. The event lasts minutes. The logistics can determine whether those minutes are seen at all. For the 2026 eclipse in Spain, the low sun makes horizon planning especially important. A site can be technically inside the path of totality and still be poor if mountains, buildings, haze, or coastal cloud block the view at the critical moment. For the 2027 eclipse near Luxor, the challenge is different. Heat, travel logistics, crowd management, and safe observation during a long midday totality. The shadow is astronomical. The experience is intensely local. The 2027 eclipse crossing Egypt will be a particular scientific opportunity because of the long totality. Nearly 6.5 minutes is enough time to conduct substantial scientific observations of the corona, to photograph solar prominences through their full evolution over the eclipse duration, and to make measurements at the edge of what is possible during any eclipse. A long totality changes the emotional experience too. 2 minutes can feel impossibly short. The eye is still adjusting. The mind is still trying to understand the corona, and already the second diamond ring is approaching. 6 minutes is different. It gives time to look, breathe, notice the horizon, search for planets, examine prominences, and return to the corona again. It still ends too quickly, according to nearly everyone who sees it, but it allows the experience to unfold rather than strike and vanish. This is why the 2027 eclipse is already important to scientists and eclipse chasers. Long totalities are rare gifts. Expeditions are already in the early stages of planning, and the Egyptian desert, with its typical summer clarity, offers better meteorological prospects than many eclipse paths. Let's come back to where we started, to the experience itself, because the science and the history and the mechanics are all genuine and important, and none of them quite accounts for what happens to people when they stand in the moon's shadow. The total solar eclipse is, in a very specific sense, the most direct possible confrontation with the solar system as a physical system. This is the emotional core of the subject. Astronomy often asks us to imagine scale. We imagine the size of the sun, the distance to the moon, the curve of Earth's orbit, the tilt of the moon's path, the invisible line connecting three bodies in space. During a total solar eclipse, the imagining stops being abstract. Scale becomes something happening to the light around you. The moon's shadow is not a metaphor. It is a real region of space where sunlight has been blocked. It touches Earth's atmosphere. It moves across the ground. It cools the air. It changes animal behavior. It changes the expression on people's faces. It makes the solar system physical in a way no diagram can. That may be why the reaction is so strong. The eclipse does not simply show you something. It places you inside the geometry. When you stand in the path of totality and watch the moon's shadow approach from the western horizon, a darkening that sweeps toward you across the landscape at speeds that dwarf any vehicle, you are not watching a metaphor or an image or a simulation. You are watching the three-dimensional geometry of the solar system manifest itself on the flat screen of the sky. The moon is there, physically between you and the sun. The geometry of the orbits has arranged itself in three-dimensional space so that you, the moon, and the sun are in a line. The corona you see, those white streamers reaching outward, is the actual outer atmosphere of the actual star that provides essentially all the energy for everything alive on Earth, revealed directly to your eye by the accident of orbital mechanics that put a moon of exactly the right apparent size in exactly the right position at exactly this moment. There is no intermediary, no instrument, no translation, no representation. The event is happening directly in front of you. This directness, the way the eclipse confronts you with the physical reality of the solar system in a visceral rather than abstract way, may be what distinguishes it from other astronomical phenomena. You know intellectually that Earth orbits the sun and the moon orbits Earth. You have known this since childhood. Knowing it and seeing it are different, and the total solar eclipse makes you see it. Ancient observers, seeing the eclipse without the physical framework we use today, experienced the same sensory event but interpreted it through different conceptual structures. The sun disappearing, the light going wrong, something happening to the sky that shouldn't happen to the sky. The terror was rational. An apparently fundamental feature of the world, the sun, was behaving in a way that violated all normal experience. The awe was rational too. Both responses are available to the modern observer who stands in the path of totality, knowing exactly what is happening physically, because the knowing doesn't insulate you from the event. The knowing adds to it. Understanding what you are seeing, understanding the geometry, understanding that you are in the moon's shadow while the rest of the world continues in ordinary sunlight just outside the path, adds layers of significance to an experience that is already affecting you at a level below the significance. This is the difference between fear and awe. Fear says the sun has disappeared and the world may be broken. Awe says the sun has disappeared because the moon is exactly where celestial mechanics said it would be, and somehow the knowledge makes the disappearance more powerful rather than less. Modern eclipse observers are not less affected because they understand the event. In many cases, they are more affected because the event becomes both sensory and intellectual. The sky darkens, the corona appears, and at the same time, the mind understands that this is an alignment of bodies separated by hundreds of thousands and hundreds of millions of kilometers, projected onto a human afternoon. That combination is rare. The total solar eclipse is a very old event in Earth's history. There is a deep calm in that thought. Human beings have attached stories, omens, equations, instruments, expeditions, and emotions to eclipses. But the event itself is older than all of that. The moon cast shadows before there were animals to react to them. It cast shadows before there were flowers, forests, or continents in their present forms. It cast shadows over oceans where nothing yet understood light as an image. The solar system was doing this long before it had an audience. That makes the human experience feel both small and precious. We are not necessary for the eclipse. The shadow would move without us. But when we stand inside it and understand it, something ancient becomes conscious for a moment. Long before any life existed on this planet, the moon cast its shadow across the surface in patterns determined by the orbital mechanics of the early solar system. In the deep past, eclipses would have looked different. When the moon was closer to Earth, it appeared larger in the sky. Total eclipses would have been more common in character and less finely balanced. The moon's black disk would have covered the sun more generously, and the delicate match that lets us see the corona in such a striking way would not have been the same. The young Earth, rotating faster, with a closer moon and shorter days, would have experienced a different eclipse rhythm. As the moon receded, the character of eclipses changed. The match became closer. The era of especially beautiful total eclipses emerged slowly, without anyone to see most of it. Long before any eye existed to see the corona was there, the hot plasma of the outer sun extending into space, the magnetic streamers reaching outward, the solar wind flowing past the dark silhouette of the moon. The eclipse has been happening for billions of years, waiting for something capable of looking. This sentence is not literally true in the sense that the eclipse had intention. The universe does not wait the way people wait. But as poetry, it points to something real. For most of Earth's history, total eclipses occurred without any mind able to understand the geometry or any eye able to appreciate the corona. Now there are eyes. There are instruments. There are people who can predict the path thousands of years into the past and future. There are spacecraft watching the sun and clocks precise enough to time the shadow to the second. And still, when totality begins, people gasp. Understanding has not removed wonder. It has refined it. We are briefly that something. We have hundreds of millions of years left of total solar eclipses before the moon moves too far away. In the context of deep geological time, that is not very long. In the context of a human lifetime, it is almost infinitely long. No one alive today will witness the end of total solar eclipses, and no one alive today can imagine the end of them, any more than they can imagine the end of the seasons or the end of tides. But knowing that the window is finite changes something about the experience. It also gives the episode a deeper ending than simple spectacle. A total solar eclipse is not rare only because it happens infrequently at a given place. It is rare because the planet itself is passing through an era when this kind of eclipse is possible. We are not just lucky to live near a path of totality in a particular year. We are lucky to live in a geological age when the moon still appears large enough to cover the sun, but small enough to leave the corona displayed. This is the kind of coincidence that becomes more beautiful the more carefully it is understood. The total solar eclipse that any of us can see, the next one accessible from where we live, the one we are already planning to drive or fly to, is not available to any generation of humans that might come a billion years from now, and was not available to any generation of life forms that might have existed before eyes capable of appreciating the corona had evolved. We are here, in this narrow window, with these eyes, in this period of the moon's orbital distance, at this moment when the geometry works. Standing in the path of totality, in the cold shadow, in the darkened afternoon, watching the white corona glow around the black disk of the moon, is standing in a very specific place in time. It is also standing in a very specific place on Earth. A person a few kilometers away may see something profoundly different. Inside the path, the corona appears. Outside it, even very close to the edge, the sun remains partly uncovered and the central transformation never happens. This sharp geographic boundary gives totality a strange social quality. One town may be in darkness while another, just down the road, remains in partial daylight. One hillside may see the corona while a valley beside it is blocked by cloud. The eclipse is global in origin and local in experience. That local quality is one reason people remember exact places. They do not simply say they saw the 2024 eclipse or the 2026 eclipse. They remember the field, the road, the roof, the desert, the beach, the schoolyard, the hill outside town, the sound of people around them, the cloud that almost ruined it, the sudden clearing, the cheers from strangers, the strange cold, the way the horizon looked. The eclipse is astronomical, but the memory is geographical. The universe happens somewhere. That is why totality can feel both cosmic and intimate. The sun is enormous. The moon is distant. The mechanics are planetary. But the memory may be the sound of a dog barking at the wrong time, the smell of grass cooling, the sudden chill on your face, or a stranger whispering when the corona appears. The scale is astronomical, but the contact point is human. Not just in the geography of the shadow's path, but in the 4.5 billion year history of the Earth-Moon system and the approximately 600 million year window during which total solar eclipses are possible. That is not nothing. It is a rare alignment of scale and timing. A star 400 times wider than the moon, a moon about 400 times closer than the sun, a planet rotating under a moving shadow, and a living observer standing in the right narrow strip of ground at the right minute. Most astronomical facts are understood from a distance. You learn that the moon orbits Earth. You learn that Earth orbits the sun. You learn that the sun is a star, that gravity governs motion, that shadows have geometry, that distances can be measured, that cycles can be predicted. Most of the time, these facts remain in the mind as knowledge. A total solar eclipse turns them into sensation. This is difficult to reproduce in video because video flattens the event. A camera can show the corona. It can show the diamond ring. It can show the darkening landscape, but it cannot make the viewer feel the temperature fall or the crowd go quiet. It cannot reproduce the peripheral awareness that the horizon is glowing all around you. It cannot make the sky feel wrong above your own head. It cannot give the body the knowledge that the sun has disappeared in the middle of the day. That is why people who have watched many eclipse videos are still shocked by their first totality. They have seen the image. They have not yet stood inside the shadow. The orbit becomes a shadow. The shadow becomes a temperature drop. The temperature drop becomes goosebumps on skin. The geometry becomes a black disk where the sun should be. The corona becomes the visible atmosphere of a star. Knowledge moves from abstraction into the body. A total solar eclipse is different. It touches the landscape. It changes the air. It shows the corona with no screen between your eye and the sun's outer atmosphere. It makes orbital mechanics feel personal. The moon's shadow is still moving across Earth from time to time, narrow and precise, crossing oceans, deserts, cities, mountains, and fields. Somewhere, years from now, another afternoon will dim. Another horizon will glow. Another crowd will fall quiet. Another black disk will cover the sun, and the corona will appear. For a few minutes, day will quietly turn to night, and then day will return, as if nothing impossible has happened. That return is part of the lesson. The eclipse does not break the world. It reveals the world as it is, moving, tilted, orbiting, shadowed, illuminated, predictable, and still capable of overwhelming anyone who stands in the right place at the right time. That is why the subject works so well as a calm space documentary. It contains spectacle, but it is not only spectacle. The final section should not feel like a summary of facts. It should feel like the meaning of the facts finally becoming clear. The geometry matters because it places the viewer inside a shadow. The history matters because humans have always tried to understand that shadow. The discoveries matter because the shadow briefly revealed things normally hidden by sunlight. The future matters because the shadow will not always exist in this form. By the end, the listener should feel that the eclipse is not a trick of the sky, but a rare intersection of physics, time, and perception. It contains history, but it is not only history. It contains equations, but it never becomes only mathematics. It begins with the body noticing that daylight has changed and ends with the mind understanding that the change was written into the motion of the Earth and Moon long before anyone was here to predict it. A total solar eclipse is one of the rare astronomical events that does not require imagination to feel cosmic. It brings the cosmic down to the ground. It places the shadow of another world across your own. Good night.